All right. Good afternoon, everyone. Great to see a full room. Welcome to this session about API security. More specifically, I'm going to talk about 7 things about API security. And in case you didn't bother reading the abstract, which is totally fine, by the way, and it's going to be about 4 vulnerabilities, maybe even more, depends on how far we get. 2 case studies showing you that these things are relevant in practice, and 1 demo to kind of make things somewhat interesting and to make you pay attention, basically, in this afternoon. All right. I hope you'll enjoy this. If you have any questions, come up after the talk or grab me when we're leaving the room. Later it's going to be hard because once we disappear into the crowd, it's going to be insanely difficult to find me again. But take your shot at the end of this session. That's my best advice I can give you. All right, let's talk about API security. Why API security? Well, I don't think I have to tell you that APIs kind of have exploded. APIs are everywhere these days. And it turns out that API security issues are also almost everywhere these days, and securing these APIs is hard. It turns out a lot harder than we've anticipated. Sometimes it kind of feels like we're taking a step backwards when it comes to security. I don't think, well, it depends on how you look at what backwards means. I think there's just so much more going on these days, and it's so much harder to secure all of that, that it kind of feels overwhelming sometimes. And one of the good indications of how things are evolving is what the API Security Top 10 has to say. This is a top 10 of the most common or the most dangerous vulnerabilities, or actually a combination of both, if you look at the ranking mechanism, and it's a document published by OWASP. And OWASP is this non-profit organization aiming to improve the state of web security. That's where the W in the name stands for web security, but it's kind of grown into AppSec in general in the last decade because mobile apps became a thing, APIs became a thing, and so on. And OWASP is focusing on all of these security aspects, if you want to call it that. And they've had a top 10 for regular web applications for almost 2 decades now, I think. And after a while, people realized a couple of years ago, like, yeah, the top 10 issues in regular web applications kind of apply to APIs, but not exactly, because some things are out of scope, some things are all of a sudden a new issue that we haven't seen in regular web apps. And that's when a couple of volunteers decided, let's build an API security top 10. And that gained a lot of traction, and we actually had an update to the API Security Top 10 this year. So if you knew about this before, it has been updated this year, and a couple of things have shifted around, have been consolidated, new things have been added, and so on and so on. And we're going to talk about a whole bunch of these issues in this 50-minute session on API security right here. And before we do that, just a quick word about myself. Philippe De Ryck, I'm from Belgium, so this is very nice to speak in my own country without traveling too much, at least in Belgian terms. And what I do is I do security. That's, in a nutshell, what I spend my time on. I run my own company called Pragmatic Web Security, through which I help developers that build actual software, help them understand security, and help them build more secure applications, through training, online courses, consulting, basically whatever you need to make security better. I'm also a Google developer expert and an Auth0 ambassador. These are recognitions from the DevRel programs of these companies about the work I've been doing for the community, writing articles, doing talks, sharing resources. So it's definitely an honor to be part of those programs. I don't work for Google or Auth0, I'm just somewhat related to their DevRel programs. And finally, I volunteer for SecOutDev, which is a non-profit organizing a AppSec course in Belgium, in Leuven. We've been doing that since 2005, I think, like a very, very long time. And it's 1 week with experts from all over the world that teach AppSec. So if you want to learn more about security, check that one out for next year, June 2024. All right, about this talk, I have a bunch of slides with some images and some text and so on. If you want to grab a copy, there's a QR code you can scan right there, or you can just find it on my website or social media, LinkedIn, Mastodon. I'm not hard to find, and I do share the links to my slides, so grab them from there, and we should be good to go. All right, housekeeping out of the way, so let's talk about security. Let's talk about how APIs are everywhere. Apparently, you can buy all kinds of connected appliances these days, and if you buy a scale, of course, you find a scale with an app connected to it. And it's not like the scale talks to the app with Bluetooth very locally, very nice and convenient. No, of course not. It talks to an API. Scale connects to an API, and the app connects to an API, and all of a sudden you have this internet-connected system, and the API is sitting out there, and the attacker can target that API, and we end up in stories like this, where the app puts a lot of people at risk. And that's essentially the best example I can give you of how APIs are everywhere and how API security has become kind of an important thing. And we're going to use this story. I'm not trying to shame them, it's just that they have a whole bunch of issues that allow me to talk about these issues and also allow me to talk about how to avoid or try to fix these issues in practice. So we're going to be talking about this story for quite a bit. First thing I want to talk about, I'm going to make things really easy. I promised you 7 things. Well, if you take that API security top 10, we're going to hit 3 of those in the next couple of minutes. We're going to talk about authorization. And what should scare you actually is that the OWASP security top 10, it's a top 10, 3 out of 10 items are related to authorization. That's a lot. And authorization is really hard to get right. And you can get it like really wrong or just a little bit wrong. But in general, when there's an authorization failure, it means somebody has access to something that they shouldn't have. And that often means stealing data, extracting data. It also means performing operations, and it can be the escalation towards more serious attacks as well. Sometimes it's like, oh yeah, they can get some data, whoops. But that whoops turns out to be like, oh, and now with that data we can do this, and with this we can do that. And before you know it, you are fully compromised and end up in one of these stories in one of my slides. All right. Seriously, I actually keep track of all of these stories. So whenever I have to build slides, I just go into my notes like, this one looks interesting, and then we take it from there. All right, so what authorization problems did they have? Well, it's a scale with an app, and you can track your weight and your progress and see it go up or down, or with the pandemic probably up and things like that. And they also have families. So you have more people in one household, so you don't have to buy a scale for each of your family members. You can just set up different users in the app, and then based on that, they can all track their own data and so on and so on. And it turns out, if you want to add or delete family members, that the developers of the API kind of forgot to implement authorization there. It's like, whoops, that's not how things are supposed to go. So one of the vulnerabilities here is the missing authorization step, which leads to worse problems down the line. We'll talk about that later on. But it brings me to a very interesting question, like why is authorization so hard to get right? I've been dealing with companies and their applications and figuring out how to make them more secure for a long time now. And authorization is one of these very difficult topics. When it comes up, there's always issues. I'm fairly certain that it will always go wrong. Even when you try your best, there's going to be a screw up at some point in time. So let's take a look at how this typically goes from small to larger and how we can try to make things as manageable as possible so we can try to avoid those screw-ups in the future. All right, let's start very simple. Code example. Has role. This is this is Java code, so one of the benefits here is everybody in the world can read it regardless of what language you program in, so that's kind of nice. It's also very verbose, which is a benefit in this case. But it's the add member, it's kind of a fictional implementation of the story we had, so we can add a family member, and in this case we do have authorization, which is good. We check if you have the role family owner in this case, so if you are like the owner account, the parent account of the family before you add a member. And that's role-based access control, and that's typically how authorization starts. Trust me, I've seen this with new projects. When a company starts up with a new project and they involve me to talk about security, of how to get it right, it starts like, yeah, we have this prototype with some of the roles, and bam, there we go. Role-based access control. Nothing wrong with this if you look at the slide right here. However, things like this evolve. And after a short while, your prototype grows and grows, and all of a sudden you have multiple roles. All of a sudden it's like we have a family owner, but we also have parents who are not necessarily family owners. And then, of course, we have like admin access to resolve customer issues, so admins can also access endpoints, and so on and so on. And this is a problem that has a very dramatic name. It's called role explosion. And it's basically because we have multiple roles with very similar permission configurations, like the roles can access similar endpoints, but not exactly the same. And we need to create a role for each of these. And these are fictional examples for PowerPoint slides, because I can't show you an authorization policy with 722 roles, because, well, that doesn't work very well in presentations. But in business applications, you notice in your company, you have very often you have a massive amount of roles. So think about how manageable this becomes. It's like if you add a new role, now you have to open up your API and go through all of your API endpoints, like, oh yeah, this role has access to this endpoint, and you write like, or has role this, and it's a mess. It's an absolute mess. And trying to audit this is also problematic. I've been on that side of the table, so when I come in, I typically ask questions until people start looking at each other and say like, yeah, we don't know. Like, how do you do that? Like, oh, like this, and how do you do that? Like, we don't know. Interesting, let's figure that one out. And if you have role-based access control, the problem is to make sure if this endpoint is safe, you need a full mental model of all the roles that exist, and you have to check whether this makes sense. And an outside perspective, if somebody like me, I can't know if a parent is allowed to add members to a family, whatever. I have no idea. Meaning you have to go back to a policy saying like, oh yeah, this is indeed intentional, and go back and forth. And this is really, really challenging to get something like this secure, to audit something like this. And there's a really easy fix. This is common, by the way. Look at any web framework you'll find to write web applications, API-based applications, you'll find role-based access control either built in or as one of the popular libraries that's available or as middleware or whatever. RBAC is everywhere. That's just the way things work. And there's a very simple fix to make your life so much easier, and that's decoupling that role information from the endpoint. And it's a very trivial change, but it makes everything so much better. And basically in code it looks like this. Instead of checking has role, you check has permission. Does this user have permission to add a family member? And all of these issues, or a lot of these issues, magically go away. Because all of a sudden, auditing code like this, anybody can do that. Add member. What does it do? Well, there's hopefully some documentation like adds a member to a family, and it checks the permission, add family member. It's like, yeah, that kind of makes sense. Check. Next step, you have to map these permissions to users, and you can do that any way you want. If you have role-based access control, users have roles have permissions, and bam, all of a sudden you can make like a nice table out of this, or you can store this somewhere else in a list or whatever works for you. But all of a sudden you have a very clear view of who can do what, and you can audit that separately. You can audit your user or permission mapping to roles and roles to users to make sure if that corresponds to your business idea of what authorization should be. And then you can check the implementation to make sure it's enforced correctly. And all of a sudden you have an authorization policy that can be audited. And that's good, because if it's auditable, then you can verify that it's secure and you can actually move forward with that. Awesome. And if you want to add new roles here in this system, easy. Just add a line in your table or database or whatever, new role, check, check, check these permissions, and bam, you're good to go. Awesome. That wasn't that difficult, right? I mean, why is authorization so hard? If this solves the problem, then it shouldn't be a hard problem. Well, so far we solved something we call function-level authorization. And if you look at the OWASP API Security Top 10, function-level authorization or broken function-level authorization, the problem there is listed as a separate entity. That's one of the three that we talked about. That's good. Fixing this is good. And to be honest, most applications kind of do something like this. There's not too often an application is like, authorization, let's skip that, we'll do it later. At least sometimes, or mostly you find something like this. And then the interesting part comes, because now you can do something like this. You can update or add a member to your family, and your family ID is number 1, and it's part of the URL and gets extracted and so on, and you can add family members, and that's good. And your permission is checked, and if you don't have permission for that, then you will not be able to do that. And then the problem comes to object-level authorization or broken object-level authorization. Because nowhere in this code do we check if you're actually adding something to your own family. And if you do this in a mobile app, and that's why these things are so hidden, if you do this in a mobile app, it's like click, 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 add a member, and it works. And there's nothing wrong with that. Until somebody figures out your API calls. Just by looking at a network traffic, by inspecting a mobile app, it's like, oh, you call this API, and in a web application it's super easy. You call this endpoint, what if I change the 1 to a 7 and send a request? And very often it just comes back like 200, okay, member has been created. Like in the scale applications I showed you before. And all of a sudden you're adding new members to someone else's family because there's broken object-level authorization. Nobody made that specific check whether you're allowed to do that for this particular object. And this seems like a silly problem to have, but it's everywhere. This broken object-level authorization is OWASP API Security Top 10 number 1 and has been since the beginning of that Security Top 10. And if I'm not mistaken, it's also number 1 in the regular top 10 for all kinds of web applications. This problem is literally everywhere. I can give you dozens of stories of how this goes wrong in all kinds of applications. How do we fix this? Well, that's where things get tricky. Because well, the rules depend on who's trying to access the application. And that's when you end up with something like this. And I wish I was kidding here. I wish this was just a PowerPoint example, like, yeah, nobody does this in practice. This is real world or very realistic, and this occurs in real world applications. So we do that functional level check, which is good. We check if you have permission, and then based on who you are, it's like, oh yeah, if you're an admin, then you are actually allowed to do that for anyone, so that's good. But if you're a family owner or a parent, then you can only do this for your own family, and so on and so on. And now you start adding checks like this in your policy. By the way, exception handling with smiley faces is not a recommendation, so do not use that as a takeaway here in this presentation. And if I use actual emojis, then PowerPoint starts flipping out, so that's a different story. Anyway, the problem with a policy like this is that, first of all, it's a mess to write, and second of all, you can't audit this. Trust me, I've been in that meeting, and if you ask questions about very detailed authorization decisions, usually there's 4 or 5 people in the room, everybody looks at one person, because that's the person that wrote that policy. You see the person thinking like, yeah, we get this data from there and that from there. Like, yeah, that's covered. Or what also happens is like, oh crap. And then sometimes, this has happened once, they whip out a code editor and they start writing authorization logic, like in the meeting where I'm sitting right there, like, yeah, let's add this check right here and maybe that's solved. It's like, no, that's not how you do that. There's no way you can guarantee that an application that looks like this is secure. And if it's not secure, then if you can't audit it, you don't know if it's secure, and you will have object level authorization issues. I can promise you that. So how do we fix this? Well, there's an additional step we take, and that's moving our policy decisions to a policy engine. And this sounds super fancy, like this is sales talk. Like, yeah, we have a policy engine, wow. And the policy engine is like, yeah, I'm going to make a decision and give you true or false, and you don't have to worry about anything else. And this sounds super fancy, and it can be very complicated, but for a simple application, it's enough as calling a centralized piece of code. Something called policy, where even Java, you can write this as a class with static functions. Check permission. And what do you give it? A permission. You give it a family that this is about and the user object, and that function will do all the checks that are necessary. And the checks will be roughly the same as you saw on the previous slide. The check will be like, hey, is the user an admin? In that case, it's fine. You can go ahead. True. Is the user a family owner? Then are they a member of this family? Are they actually the owner here? Like, yeah, okay, yeah, sure, and we can move forward with that. And that's essentially how you can move this to a policy engine. And it sounds super fancy, but this centralizes your authorization logic, and it has so many benefits. First of all, you can ensure that pull requests don't just update the authorization logic at will. You can block that and say like, no, we have to think about whether we actually want to update this. You can audit your authorization logic, make sure that it's correct, that it does what it does. You can write unit tests against all of these functions to make sure that your policy behaves the way you think it behaves, and your life will get a lot better. And now all you have to do is you have to have a rule in your code checks that says like every endpoint checks this policy, done. And you make that problem a hell of a lot easier to manage. And then, if you want to, you can move a step further, and you can use an actual policy engine instead of just your own version that you whipped up, but something like Open Policy Agent, which is software that allows you to write a policy in a policy language and then reason or call that policy to ask for decisions. And it can be super simple, but can be super advanced as well, rely on any data you feed into it, any request data, tokens, fetch additional information, and so on. And so on. But this is not necessary to benefit from that centralized authorization logic. And the first takeaway I want to give you here is that you have to really look at centralizing this authorization logic. Having it spread out through your API, through your routes, to your endpoint definitions, it's not going to work. That is a recipe for failure. Maybe not now, but somewhere down the line. At some point, somebody's going to make a mistake, and you can end up in trouble. Second takeaway for this section: empower auditability. And that's really important because you have to be able to assess the security of your policies. Just writing it is one thing, but having the option to go back to it maybe half a year, 2 years later and decide like, is this secure? Does this do what we want it to do? That should be possible. Somebody new starting should not be spending 2-3 months figuring out how you handle authorization. It should be intuitive, it should be logical. And that is going to help you secure your applications. back to our smart scale application. There's some other issues there as well. One of the issues was that the server, or the API in this case, leaks somewhat sensitive values. If you're in, I did a session on OWASP on Monday, and we talked at length about access tokens and refresh tokens and so on. And it turns out that these are leaked from API responses. Something that's not really supposed to happen, but whoops, all of a sudden there's some extra data in that response. And this is called sensitive data exposure. And in the OWASP API Security Top 10, it's listed under a denominator called Broken Object Property Level Authorization, or BOPLA, which is abbreviations. It's going to go God knows where, but that's where we are at now. And how does this happen? Well, sensitive data exposure is a kind of a silly problem to have. And it's basically an API giving you too much information. I'm going to use a very simple example here. My simple example is the API Security swag shop. So you can buy stuff here, and it has a list of online users. And the whole idea is that we get that list from an API endpoint, because we're building API-based applications, and it's going to get a list with users, with IDs and names, and we display those names. Don't ask me why, that's just the example, so let's roll with it. However, we can see in the response here, there's also address information for all of these users. We're just sharing that address information, but never rendering that on the page. And that's sensitive data exposure in the world of APIs. It's that responses often contain so much information that the front end, the client never uses, but it's there. And if you would read about problems like this, you'll often encounter text like, but to access the data, the attacker would need access to the encrypted traffic to observe the responses. It's like, okay, yeah, that sounds very difficult. How would you do that in a web application with an API? It's like, open DevTools, click on the network tab, and whoop, there it is. There's all your encrypted data sitting right there. And I'm not joking. I wish I was joking. But that's the reality of accessing this data, just looking at the responses. The JSON responses are there, the data is there, and anyone who's running a client can access that data. And on mobile, the first thing a mobile pen tester will do is hook the phone that they're using up to a proxy and observe all the network traffic that's being sent by the client as well. There's tools to do this, very straightforward to obtain that traffic. And when there's sensitive data there, especially for objects that are not yours, then we can of course extract that data and do whatever you want with what's there. And this has happened to a lot of companies over time. So where does this problem come from? How does this happen? One of the most common ways for this to happen is when you're using your models directly in your responses. So here's a very simple example, again Java, so you can actually read it. And we have a user object. We just return a list of users. User objects have an ID, a name, and an address, and you can see where this is going. This gets automatically translated into JSON with all the fields of the object. That's how this goes. Very straightforward, very logical. Unfortunately, very, very common. How would we fix this? Well, one way to fix that would be to mark certain fields as ignored. Just giving you this as an option, because that's what people often resolve to, like, yeah, let's just mark some fields as hidden, and the problem kind of goes away. But it really doesn't, because this, again, is trying to block things instead of only allowing what you want to allow, and that's not really a good practice. So this is not a deny by default practice. This is useful if it's one field. If you want to do this across an entire API, it's not going to work. And a better solution would be to use something in the line of DTO. Data transfer object, a very old pattern that is still highly relevant in applications today, which has different ways of implementing this. You can do it very verbosely with an actual object. You have schema-based solutions in different languages as well, whatever works for you. But now you're sharing public user info. Your application becomes easier to audit because you can check the endpoint. What are we returning? Public user info, what's there? An ID and a name, like, yeah, that makes sense. We want to share that. Good, off we go. Again, that auditability is important there. And this hooks up to things like OpenAPI specifications, where you write the spec of your API, you define what fields are present in the response, and you can check those specifications against your APIs to make sure you adhere to that as well. That's sensitive data exposure. Present in the security top 10, number 3, if I'm not mistaken. So a significant problem in a lot of APIs. Where do you get those DTOs from? Well, that's where things get tricky again, because I've seen people I've worked with people who are like, yeah, we're using DTOs. It's like, okay, can you show me? And they open it up, and the DTO contains exactly the same fields as the model. It's like, where do you get those? Like, oh yeah, we auto-generate them from the model. It's like, but that's not how this doesn't give you any benefits. That doesn't work like that. So be careful and either write these yourself, generate them from your OpenAPI spec. That's fine if you have checked that manually that spec is actually what you intend to share, then this might work in practice. But again, be very mindful of where you get this and how you get this done. And that brings us to avoiding sensitive data exposure, something that is really, really common in modern APIs as well. Actually occurs in a variety of features. So one of the stories I haven't included in the slides here, but one of the stories where this occurs is in Grindr, a dating app, where you actually could reset your password. And one of the sensitive fields that was being exposed when you did that was the actual password reset token. Just there in the response, not used in the front end, but there in the response, all it takes for you is ask for a reset token for my account, look in your network tools, find the token, submit it, and you could change my password just like that. To give you an example of where it can occur, this is actually quite a common problem as well. Back to our gift that keeps on giving, that smart scale. So if you want to buy Christmas gifts, maybe this one is not a good idea. So unless you're buying this for a security researcher, then this is a very nice hobby project. Otherwise, I would be careful with something like that. Same goes for fridges and washing machines. And if it says connected to an app, just don't buy it. That's probably a safe approach to go forward here. What's the problem here? Another issue, and this kind of relates to the problem where we could add family members to an account. So the lack of authorization on adding family members would basically mean that I, as an attacker, can add one of my accounts to your family. And one of the data fields that gets leaked is the owner or the parent account for that family. So all of a sudden, I have a reference to your account for your family. And that account I can use as input in the forgot password functionality, where I could actually use or abuse the application to break or to reset your password, which allows me to do a full account takeover on your account, just by chaining these vulnerabilities together. And for this example, I promised you a demo, so we're gonna talk about breaking authentication. The example is based on the story from the smart scale, so we're gonna use a password reset feature. I'm gonna do some username enumeration attacks as well, where you can verify if a username exists. And I wanna give you a disclaimer. The demo looks surprisingly simple, but the goal here is to show you how easy it is for attackers to do this. Because very often, people think like, yeah, but that's a very sophisticated attack, like nobody's smart enough to do that, will come after me. But these attacks are super simple. If you know how to do them, it's straightforward. And one of the good things is I'm going to show you exactly how to do them. So if you want to do it against your own applications to convince your boss that something is important, then you can do that yourself as well. Do not do this on other applications. That's not how things work legally. So you're not allowed to do that unless they're part of a bug bounty program. Then it's fair game, of course. All right. For this, I'm going to use a tool called Burp. Burp is a pen testing tool that you can use to observe application behavior and to perform certain types of attacks. And one of the ways to observe application behavior is by using the Burp proxy and by clicking the Open Browser button. And that's going to launch a Chromium browser that will send all of its traffic through Burp. So we can look at the requests and the responses. So sensitive data exposure becomes really easy to exploit because you can just click through it and see what is present in those responses. All right, so my app is running on Restaurant. It's a restaurant review app. There's not much to see here except for the things we're going to abuse, of course. And in this case, we have a traditional login form that we are potentially interested in. Of course, in reality, it's not filled out with your demo account, but that just makes my life a bit easier here. So what happens? We can log in. And if you log in, we end up here. Like I said, not much to see here. We can log out again, of course. We can log in as a user with the wrong password. So if we enter something else here, that doesn't work. Okay, that's good. And we can log in as a user that doesn't exist. That also works as expected, as in it fails. So that's kind of a good thing. If you go to Burp, you can now see in the history, you can see exactly what the application has been doing. So this is calling an API, the login endpoint. You can see that the first one succeeded, we get an email and my password, my very not so secure password is right there, and you can see the response and so on and so on, and you can see it failing right here. One of the attacks is called username enumeration, and one of the goals with username enumeration is figuring out if a user exists in your application. Why is that useful? Because then you can start launching targeted attacks. Depends if this is a public app, you can figure out which account exists and then start sending like spear phishing, like, hey, your account on this application with some details, blah, blah. Or you can try to perform other attacks like account takeover, as we will do in a second. So how do we do that? Well, one of the ways to do that is if the error message on the right, so invalid email or password, if that error message is wrong. So if it's different for a missing account or a wrong password, that's a very clear giveaway. That's like, ooh, this account, the password is wrong, and this account doesn't exist. But in this case, that's not true. So this one is, the account doesn't exist, and the password here is wrong, but the error message is the same. Second thing that happens, let me show you the code here. Second thing that happens when we log in, this is where we are in the application code. So you can see here the error message, if the user doesn't exist, is invalid email or password, and if the password doesn't exist or is wrong, then we say the same thing. That's a security best practice. By the way, I did generate a demo with ChatGPT and it got this right. So that's a good sign. Given all the AI code stuff in the vendor boots, this is a good sign that it actually got that right. It warned me about it, like you should not give out different error messages, so that's good. What's the next step? Look at the code here. If the user doesn't exist, we return an error message. If the user does exist, we go forward and we check the password, and if that's wrong, we give an error message. Checking a password is using a library called bcrypt, because if you know a bit about password storage, you should not store them in plain text in your database. That's a bad idea. We've been over this for a long time, so I'm not going to talk about password storage. The thing about secure password storage is it takes a while to verify because it should be resistant against brute force attacks. And taking a while means observable behavior. So what you can do as an attacker is you can just try things, and let me see if we can see this right here. No, I'm not sure if there's a column here for response times, but typically when you have to verify a password, it takes a little bit longer to get that response than when there's no password to verify. And that's something we can abuse to figure out if accounts exist. So let's launch an attack like that just to see what's going on. So what we do is here we send this to the intruder, which has a very ominous name, but that's kind of what the tool does. It allows you to launch attacks, brute force attacks typically, against the target application. I can see burp here. Burp already suggests like, hey, this is a variable, and this is a variable. Do you want me maybe to insert some other values there and see what happens with the backend system? It's like, yeah, let's do that for the email address. We don't care about the password. It can be wrong. That doesn't matter. So we don't care about the password, but let's insert this email. Let's insert some other values there. What do? Well, we provide a list of email addresses to insert. So let me copy paste that from my list here. So let's see if one of these accounts exists on the application. In reality, you do that with names you find on LinkedIn for your company if it's a company application, or just some stolen email list from the Facebook Messenger breach or whatever. There's so many lists that you can use. So we can paste this right here. So now we have the values that we will substitute. You can see at top here, it's a request count of 7. We do not want to encode this, it's JSON. And yeah, that's it. So let's start the attack. And you can see that all of these fail, which is kind of expected. We just throw random email, well, not random, we throw email addresses with a random password. If that would succeed in an authentication, that would have been interesting. But if you look at the response times, you can see this column right here. You can see that one request took 800 milliseconds to complete, and the other ones took like 10 to 13 milliseconds. Guess what that is? That is that password hash that's being done because this user, the victim, which is kind of predictable here, but whatever, that victim actually has a valid account. So now we learned that this account exists, which is very useful information for our second step, but this works really well against all kinds of applications, by the way. So this is large enough, that number, to be observable over even a less reliable network than a local host, and that's something to be definitely aware of. Let's first try to fix this, just for completion. We can fix this by making Both code paths last more or less the same, at least make it less observable. And it's basically as simple as adding a fake password check right here. And I'm going to cheat. I'm going to copy paste this. So we could do something like this. If the user is not found, let's just spend some computing power. This is not the most economic way of solving it, or environmentally friendly maybe. But you need to make sure the requests spend as much time as you can. You can, of course, work with sleep or whatever if that's more efficient. But just to give you an idea, if you make those code paths last as long, the attack becomes less easy to perform. All right. Username enumeration. So we now learned that this account exists. So let's see what else we can do. Let's go back to our application. What we really want to do is we want to reset the password for that victim account. I've given it a random password. I don't even know what the password for that victim account is, so we can't really log into that. But we can do that as a legitimate user for our account. So let's investigate what's going on right here. If we reset our password for our account, it's like, okay, we got an email. So let's go to our email. Fake email, by the way. Here's your password reset link. It's like, okay, we all know how this works, right? And if you click that link, you will be taken to a page to reset your password. What can you see here? Probably not much, regardless of the size of the screen. There's a code, a password reset code, right there in the email. And it's 4 numbers, 6452. Wow, that looks good. So let's click that. And we can choose a new password here. So let's use test. And reset our password. Done. All right. Log in with your new password. The old one doesn't work anymore. So it actually updated the password, and the new one works. All right. Yes. Awesome. Thank you, ChatGPT. Seriously, for building demos, this thing is a godsend. I just write some crap, and then I throw it in ChatGPT. Use Bootstrap to make it pretty. And off we go. That's 2 hours of my life saved. Anyway, I still built my slides myself, so for now. Let's no, seriously, the moment it starts getting a little bit more complicated, it starts screwing up. So it starts inventing stuff, and it's like, no, that's not how things work. But all right, let's take a look at the password reset stuff right here. This is the request to reset a password. You can see a call. It's a post request to /API/reset password, very unsurprising. And you can see that we provide the code there. That's 6452 along with a new password test. And we get a response that says like, yeah, we set a new password for the account. It's like, okay, 4 digits, I think we can attack that. So let's take a look at, to show you again how easy this is, we send this to the intruder. By the way, the scale I've been using as the example, they use a little more sophisticated mechanism here. They use 6 digits. So that's at least 2 factors of magnitude more complicated, which also makes it very hard to do a live demo. So I chose 4 because that actually works in a live demo. So let me send this to the intruder. There we go. We want to use a password that we actually know. So test is a good password, and we want to replace this code with something. So that's good. Payloads. This is a number, and we should start at 1, and we want to go all the way till 9999. So that's good. Steps 1. Let's use 4 integer digits and 0 fractional digits. That's good. Which account do we want to do this for? The victim account. So there's one important step that I'm very happy I remembered. We first have to create a token for that victim account. So go here. We're still logged in as our account, so log out. Reset the password for victim at virtualfoodie. That's my other demo application, virtualfoodie.com. Reset password. And this sends an email to the victim account. So if that's your account, you will now have an email, but you're of course paying attention, so you're not checking your email. So that's good. So what we will do, the code is one-time use only. So what we will do now is once we've primed the database with the codes, we can start our attack. And here we go. And it goes really fast, as you can see at the bottom, until like 7,000 or 8,000, and then it stalls a bit. But what we can see in the status code is already enough. There's 1 200. And if you look at the response data here, the new password set for Valerie, which is apparently victim at, we already found it, so it was 3,249 apparently. So if you now go to our application as the attacker, we can go to the login form. Login form, thank you. Oh yeah, it's probably because the attack is still running. There we go. We're finished. Victim, and the password was test, and we can now log in as the victim, which is not very surprising. I know the result is underwhelming here, but this is to show you that an attack like this is trivial to execute. As in, it's point and click. You don't even need. You can write code for this, but you don't even need to do this. You can just point and click and basically attack a lot of applications this way. The scale head is for 6 digits, so it would take you like a few minutes to get through all the options. And maybe if there's, if it's over the internet, you want to do it a little bit slower. But in the end, it's just a very straightforward, trivial attack. How can we fix this? Let's talk about that. The attack is maybe one part of the story, but fixing it, the problem is that we are relying on codes that allow tampering. We're relying on number values. Okay, if you want to use long and random identifiers like UUIDs, it would be a bit better because the UUID is large enough so you can't really iterate over them in general. For the scale, it would also mean you could the codes were not removed. If you add a new one, the old one is not removed, so you could keep adding more and then trying more here, and maybe you'll find something as well. But the best solution for problems like this is just take away the value that you can tamper with. If we would remove that value and make it something that the attacker can't change, then the problem would kind of go away. And the fix for that is at the top here. So the generate and verifying codes, I'm going to go from codes insecure to codes secure. Don't worry, I'll show you what this means. The insecure version is a very insecure number generator, ChatGPT by the way, so that's not very good, but 4 digits, we don't care about that. The secure one is going to use JSON Web Tokens. And I'm saying JSON Web Tokens because it's very easy to implement. Just any signed data would suffice. Any signed data would allow you to basically provide data like the email address of the user and an ID, and nobody would ever be able to tamper with that. And then, of course, we generate the token, we verify the token, and so on. That's not rocket science right here. But what happens if you do this for if you reset the password for our account here, if we go back to our webmail application, you can see that the password reset link is now a little bit longer, but the values right here, that's a signed JSON Web Token. And signed means that if somebody would change something in that token, like the email address, all of a sudden the attacker or the application would reject it because you can't provide a valid signature for that. And if you would decode this on something like jot.io, I've been here a few times, so I know where to click. If you do verify this, you can see that it has an email, it has an expiration time, so it expires in an hour, and it has a unique ID and so on, but you can't change any of those values without it being detected. And that kind of solves the problem. And this is something you can use for all kinds of parameters that travel over an untrusted channel, over an email, URL, stuff like that. And this would solve a whole bunch of these issues in practice. All right. We can check off the demo from the list as well if you were keeping track. All right, some takeaways. Avoid leaking information about whether user accounts exist, leaking additional information, because this can be used to launch attacks. And by itself, it's not a big problem. By itself, the fact that an attacker knows that an account exists is only a minor issue, but it can lead to other problems down the line. So if you can avoid this, this is a good idea. If it's public data anyway, if you have a company and everybody can guess the email addresses, then maybe this is less relevant and you want to focus on the other things. You want to implement rate limiting. This is not the first time that a 4 or 6 digit code is being attacked. Facebook had issues, or Instagram had issues with SMS reset codes, which are also 6 digits and which could also be brute forced. So you need to implement rate limiting, which is easier said than done because rate limiting is not an easy problem to solve and not a problem we can solve definitely, for sure. It's a fuzzy mechanism, like you can try and detect abuse, but it's always finding that line of how far you can push things. But what you can do is you can mitigate guessing attacks. You can stop exposing values that an attacker can tamper with, even if it's a long and random value like a UUID. Stop it. use a signed value. And JOTs, JSON Web Tokens, are a very easy way to get that signed value. Every language in the world has a JOT library. Use one, generate a signed value, verify the signature when it comes back in, and this whole problem class goes away because the attacker can no longer change a single bit of that value. And that makes things better. All right. 5 minutes. Let's see if I can cram one more into this 5 minutes. It's going to be tight, but we'll see where this leads us. Something completely different, no authentication, no authorization, but infrastructure. You have a perimeter, a firewall, whatever, something dividing the scary outside world from the pretty nice internal world. And we try to tend to believe that this internal world is actually like the image here. It's a cozy place, it's a nice place, everybody's happy and everybody's safe there. And of course, on the internal world, we have our application stuff, our internal services, and on the outside, you have the attacker. And that brings us to a very important moment in this presentation. That's a security confession. We've all done this, right? We've all reasoned about that internal world, like, yeah, we know we should probably make this a little bit more secure, but you know what? We trust our people. We're all internal employees here, our colleagues, they're not going to attack us, so we can probably be a bit more lax with security here. It's not that important, right? I'm not going to ask you to raise your hand. Confession is supposed to be private, but I'll do it for you. Yes, we've all done that. Even I've made that logic. That's a very normal way of reasoning about these things. But today, in modern applications, the attacker isn't only on the outside. The attacker will easily get on the inside through legitimate application features. And one of these problems here is called server-side request forgery, SSRF. And it goes as follows. The attacker sends a request to one of your legitimate applications running in your nice little perimeter, and all of a sudden that application is going to make additional requests on behalf of the attacker to localhost, to internal services, to whatever. This is a really common problem. It's so common that it has been taken into the regular OWASP top 10 and the API security top 10 as a new issue in the last couple of years. Server-side request forgery. And it's basically abusing a legitimate application feature where the application is supposed to make a request, except the attacker can control where it goes to. So for example, an image fetching service. You provide a URL and the application is like, yeah, I'll use that URL to fetch an image. And legitimate use cases would provide a URL, for example, on image.example.com, and the application would fetch that and return some result, and off we go. Easy, straightforward. And then the attacker comes along and is like, yeah, but just load it from anywhere. Like, load it from localhost with a weird port and bam. All of a sudden, a request goes out and we are in trouble because the application fails to restrict where that request is going to. Again, if you put it on a PowerPoint slide, that's a silly problem to have. Occurs in all kinds of services, image loading, link previews. If you post a link on LinkedIn, it will fetch it for you and show some information there. Prime example for server-side request forgery. Ask it to fetch something from localhost somewhere and see what happens. Who knows what you'll get. Can result in sending requests to internal hosts, leaking data from token services, leaking credentials, all kinds of nasty security problems. And my question is, why do we have this problem? Like, how hard can it be? This is valid data. Yes, we want to load an image from mycdn.example.com, and we don't want to load something like this. I mean, you're developers. We can probably figure out a way to do that, right? Well, wrong. Otherwise, it would be a great conclusion like, yeah, of course, it's simple, go fix it. Turns out that getting or understanding this is a lot harder than it seems because URLs or URL parsers have different opinions of what they like to see in a URL. And here's one example from research from about 6 years ago that still bites people to this day. And it turns out that if you feed a URL like this with 2 @signs, which is not really supposed to be the case, the @ is for like adding a username and a password in the URL. But if you feed it with 2 @signs, most languages at the bottom will think that this request goes to google.com. So if you write verification logic that says like, hey, this request, is this something we want to allow? Oh, it goes to google.com. Yeah, okay, that's good. And then when you send it with curl or libcurl, curl is like, yeah, let's send it to evil.com. Why not? Seriously, that's all it takes. You check it, you do what you need to do, and bam, you get bitten by that. And this is exactly what happened at Dropbox. they had the exact problem like this. They have a code check that sees one thing, and then curl sends a request somewhere completely else. And that is server-side request forgery. Fortunately, it wasn't a breach. It was a bug bounty program where somebody reported this, and Dropbox said, like, yeah, it probably would have been fine given our internal architecture, but good find, we'll pay you anyway. And they fixed this. There's a couple of fixes, and that's going to be the last part of this presentation. They fixed it by hard-coding the host of where the request is going to, because it was supposed to be their CDN hosting your images for branding purposes and so on. So they said like this block cluster, let me highlight this block cluster right here, authority is block cluster, that is a hard-coded host and the problem goes away. The attacker no longer can control this, and that was good enough for Dropbox. What else can you do? Well, if you remove ambiguity, the problem goes away. The whole issue here is that we have the URL is being parsed in two places, once for checking, once for sending. And if you can bring that to one URL only, you check the same value in both places, this whole problem goes away. What you can do is, you can basically accept the URL as input, that's line 1, the rec.body.url. You then parse this in a URL, that's line 3, and then in line 5, you recompose the URL based on this one particular view of this one parser. And whatever the parser sees, that's what you're going to use for everything else down the line. Your check and your fetching. And this would solve this problem because, well, Node.js in this case would see google.com from the URL in the example, and you will use google.com for the checks and google.com for sending the requests, and you have made this problem better. A simple pattern that actually solves the whole issue by removing that ambiguity. And that's what you are supposed, or how you can handle or tackle server-side request forgery. All right. Don't underestimate this. This is a real issue that can have some really nasty consequences. And with that, let me quickly wrap it up in 1 minute before they kick me out. We've talked about the OWASP API Security Top 10. We talked about a couple of these issues, and we actually touched upon, we haven't covered everything in depth. There's absolutely not enough time to do that in a single session, but we've covered or touched upon a few of these items and what it can mean for your applications. I've tried to give you some real-world examples to illustrate that these things look ridiculously simple on a PowerPoint slide. That's kind of the purpose of me explaining them, that they look simple, but they are really, they occur in practice and they can really come back to bite you. So 3 takeaways. The best authorization policy is understandable and auditable. You need to be able to verify the security before you can assert the security. Analyze your APIs for data leakage and brute force attack factors to avoid issues as we have shown in that demo right there. And perimeter security is not a bad thing. You can definitely rely on the perimeter as a security or the first line of defense, but not the only defense. Internal systems need to be protected. Internal systems need to be secured just as much as outside systems, because today the perimeter is easy to breach in a variety of ways, as SSRF is only one of these examples. All right. Thank you very much. Enjoy the break and the rest of the conference.